What we want to look at now is how to predict the angle in which light will either enter or leave a medium. What we saw in our labs is when light traveled into a different medium, it either bent towards or away from the normal. This is called our angle of incidence, which we are going to call theta 1. It's going to be measured between the normal and the incident ray. And theta 2, our angle of refraction, will be measured between my refracted ray and my normal. What we discovered in our labs is that the ratio of the sine of the angle of incidence over the sine of the angle of refraction was actually constant. And this constant helped us to determine the index of refraction. So if we see here, what Snell proposed in Snell's law is that sine theta I over sine theta r is constant, which is the ratio of the index of refraction over the index of refraction and the index for the incident material. Well, what is the index of refraction? Index of refraction really is just the ratio of the speed of light. And the speed of light in a vacuum is constant, and that's given by the letter c. And c is determined as 3.0 times 10 to the 8 meters per second. That's the ultimate speed of light. Nothing can travel faster than that. Well, v is the speed of light in the new medium, so in water, plexiglass, or whatever it's traveling in. Now that speed will always be slower than the speed in a vacuum. So n is really our constant, our material constant. And so we would say that the first index is n1 and the next index is n2. And what I want to point out here is the larger the index of refraction, the greater the change in direction. So conceptually, what does that look like for us? If we jump over to the other side here, we can see two examples. The first one is traveling from air into diamond. Now the index of refraction for air is given as 1.0003. The index for diamond is 2.42. Now you'll always be given these or a way to calculate them. So if we look here, it's traveled from a less dense into a more dense. It's a bigger number. So what we observe is that it bends towards the normal. If I go from air into ice, index for air is 1.0003. Ice is around 1.31. Again, you'd be given these values. Notice that it still bends towards. My angle of refraction is less than my angle of incidence, but it bends less than if it's traveling in diamond, which has a higher index. So Snell's law can take the look like this. Now what I suggest is that you add this to your formula sheet. It's written a little bit differently, so you might want to look at this. And notice all of them are ratios. All of these ratios are equal to the same constant, but do notice that for the last one, it's n2 over n1, where the rest are 1s. So just be aware of that. So a couple examples using this new ratio that we've discovered to predict. So example number 1 says, if the index of refraction for diamond is 2.42, what will be the angle of refraction in diamond for an angle of incidence in water of 60 degrees? So there's a lot there. And so the first thing we're going to do is we're going to draw a diagram and make sure we understand where everything is. Now normals will always be drawn as a dotted line, and that solid line is my medium. So it's traveling from water. N1 is 1.33, and it's traveling into diamond. So N2 is 2.42. So if we look at this, I'm going to draw my ray coming in. It's going to strike the boundary, and looking at this from our conception, it's going to be bending towards because it's going into something more dense. So it bends towards like that. Well, this is theta 1. That's my index of my incident angle, and this is going to be theta 2 here, my refracted angle. So looking back, it says incident in water of 60 degrees. So what it's telling us is that theta 1 is 60 degrees. And we want to know what is theta 2. Conceptually, we already know that theta 2 will be less than theta 1 because it's traveled into something more dense. So we're going to write it out, and I prefer to write it as index of refraction, but let's write it the way that it's given first of all. So sine theta 1 over sine theta 2 is equal to, and notice we're talking about different index of refractions, so I'm going to write it in terms of n2 and n1. Well, nobody likes working with fractions, so if we write it this way, n1 sine theta 1 is equal to n2 sine theta 2, everything is on the same side. So n1, this is medium 1, this is medium 2, so n1 is 1.33 sine theta 1, which is 60, just taking everything off my diagram, is equal to n2, 2.42 sine theta 2. Well, let's do it in two steps. Let's first solve for sine theta 2. So sine theta 2 is equal to 1.33 times sine 60 divided by 2.42, which will give you a decimal number, 0.476. Now you're going to do second function sine to get the value. So we'll take the inverse sine of it, and theta should equal 28 degrees. Why don't you pause the video right now and just make sure that you can get that number in your calculator. Now the next type of example that we want to look at is one where it travels through a number of mediums. So if we look at example number 2, it says a beam of light strikes the flat glass side of a water-filled aquarium at an angle of 40 degrees to the normal. For glass, we'll use n as 1.5, and it asks what angle does it enter the glass, and then at what angle does it enter the water. So if we look at the path in which the light takes, it is traveling from air into glass into water. I'm going to say that this is boundary number 1 and this is boundary number 2. Well, what really is going to happen is light is going to be refracted twice. It's going to travel from air and travel into glass, and glass is more dense than air, so we would expect that it would bend towards the normal. And then it's going to travel into water. Well, let's look at our table and figure out what is the index of each one. Well, air, we've already talked about, is 1.003. Glass, they've told me, is 1.50. And water is 1.33. So when it goes from glass into water, it's actually going to bend away from the normal. So we'll draw little arrows to indicate the direction of travel. And we're going to do our calculations twice. We're going to look at boundary number 1 first, my air to glass interface, and then after that we'll look at my glass to water interface. So let's first start at boundary number 1. At 1, we have n1 sine theta 1 is equal to n2 sine theta 2. So n1 is going to be 1.0003, and it tells me that it strikes it at an angle of 40 degrees. So that's always between the normal and my incident ray. So that's going to be 40 degrees. I'm looking for this one here, which we'll call theta 2. So 1.0003 sine 40 is equal to my second medium, 1.50 sine theta 2. Again, I'll let you do the math, but we'll find that theta 2 should equal 25.4 degrees. Well, if we use our geometric identities, we can see that alternate interior angles are equal. So this top angle, theta 2, will be the same as this bottom angle down here. So this should be 25.4 degrees as well. Let's call that theta 3. So at boundary number 2, we find that n2 sine theta 2 is going to equal n3 sine theta 3. So this angle here is what we're trying to find. Oops, pardon me. This angle here. So since these are equal, we've called that theta 2. Okay, so N2 is 1.50 sine, and those two angles are equal, so it will be 25.4 degrees, is equal to my new medium, which is 1.33 sine, and the angle it enters the water at. Again, I'll let you do the math, but you should find that theta 3 is 29 degrees. And that's what we expected. It bent away from the normal. Now the last lab that we did was investigating what the critical angle was. And we defined the critical angle as the angle in which total reflection first occurs. And what we also observed is that the ray actually was refracted parallel to my boundary. And so the formula for the critical angle is sine theta c is a critical angle, is going to be the index of refraction that it's heading into, n2 over n1, where it's coming from. Now for this to work, it must travel from a higher index into a lower index. So something more dense into something less dense. So we're going to write that as n2 must be greater than n1. And so that's that right there. So now we have a formula to calculate what is the critical angle for various things.